Greetings. Welcome towards the lecture series on structural analysis. In today's session, we'll be starting with the structural mechanics 2 as per the syllabus recommended by Dr. Babasaheb Ambedkar Technological University, Loneri. Before going towards the inside of the subject, let us have a course view of the subject. Course defined by the university is BTCVC 502. Course name is Structural Mechanics 2. The credit allotted to the course is 3. University has defined some examination pattern for that. It consists of Predict Test 1 and Predict Test 2 having weightage of 10 marks individual, and then followed by the mid-semester examination which is having a weightage of 20 marks. At the end of the semester, university will conduct end semester examination having weightage of 60 marks. In all, the total weightage is given is 100 marks. The total syllabus has been divided into 6 units starting from unit 1 to unit number 6. Unit number 1 deals with the analysis of trusses, in which students will be made familiar with the determinate and indeterminate trusses, analyzed with the help of energy concept, determination of settlement effects and pre-stress on the trusses. Unit number 2 deals with the moving loads and influence line, where students will be made introduced about the moving loads acting on the structure, the concept of equivalent UDL, followed by the concept of absolute maximum bending moment and shear force. The students will be able to prepare influence line diagram for determinate and indeterminate structure, addressing the shear force, bending moment, deflection and reaction over the beams, frames and trusses. Unit number 3, it deals with the cables, suspension bridges and arches, where a student will be made familiar about the types of cable, the forces in cables, suspension bridges with 3-hinge and 2-hinge girders, analysis of 2-hinge and 3-hinge arches. Unit number 4 and 5 depends upon the flexibility, application of flexibility and stiffness coefficient to the determinate and indeterminate structure, where we will have the matrix analysis to solve unknown equations using the components of flexibility and stiffness. Unit number 6 deals with the finite element method, where there will be basic introduction of finite element method, where the stress will be given towards the introduction of finite difference method, discretization method, types of element used for 1-dimensional, 2-dimensional, 3-dimensional structures, plane stress and plane strain problems, approximate solution, and variational methods are likely to be used for the analysis in finite element method. Let's go in detail. Before that, so I have listed some recommended books related to the subject and the content which we have to cover in this particular session. The recommended books are R.C. Hibbeler, Structural Analysis, publications are Pearson, Wang C.K., Statically Indeterminate Structure, publication is McGraw-Hill, Reddy C.S., Basic Structural Analysis, Tata McGraw-Hill, Pandit G.S. and Gupta S.P., Structural Analysis, a Matrix Approach, Tata McGraw-Hill, and Chandru Patla, T.R. Belegunda A.D., Introduction to the Finite Elements in Engineering, published by Pearson. Okay, before going towards the analysis concept, let us have work on a prerequisite understanding of the structural behavior. The very first question comes, what performance is expected from the structure? So here, if we want to list what the performance we want from the structure, it can be stated as stresses must be within the limit, deflection must be within limit, structure must be stable, structure must have adequate life, structure must not vibrate dangerously, structure must be easy to maintain, structure must have pleasing appearance, structure must be easy to construct, structure must have enough ductility. Let us go towards the insight of individual statements here. Stresses must be within limit. As we know that whenever the structure is subjected to load, there is a development of internal forces, and this internal action depends much more on the material content and the response of the material. If the material is elastic in nature, it will remold and it will show the larger response compared to a brittle one. So generally it depends upon what content of material we have or what type of nature of material we have. To illustrate this, I have taken an example of a tensile test of a mild steel bar and a tensile test of a taut steel bar. If you go towards a tensile test of mild steel bar, after application of gradual loading towards it, at a certain point where it reaches its yield point, the material is not able to carry much more stress, but it goes in a plastic zone where it shows a extension for a larger time period, and suddenly it get breaks at a particular interval. The point at which it get breaks down, we call it as a breaking point, and we say it's a plastic yield point, ultimate break point. Okay. But before that, we see that there is a convergent or I end generated here, which shows there was a significant reduction in the area before the yielding. So here we see that there is a certain elongation. Material has a property to show certain ductile nature. Here it's going to have more strain compared to stress carrying capacity. That's why it will give a warning behavior before the failure. So in case of ductile material, it will show me a certain linear non-linear relationship where from which I can predict the behavior of the failure pattern of the material. In vice versa, if you go towards a brittle material, what we see that material suddenly breaks down into two pieces. Thereby, it's not going to give me any warning, but it shows me a slip zone, and gives me ultimate capacity. So what a designer should have, or analysis should have, he should restrict the material stresses within the permissible limits. That is within the permissible, whether it is a elastic limit or it is a plastic limit. In the similar fashion, deflection must be within the limit. When we apply loads on the structure, each fiber of the structure gets stressed up. There is a capability of each fiber to go for a bending up to a certain limit. After that, if we remove the load, it will regain its original shape. But sometimes what happens, the load is exceeded beyond the limits, the structure goes for a permanent deformation, and this permanent deformation will cause the threat to the strength as well as threat to the stability of the structure. That's why we have to limit the structure up to a permissible deflection. The stability may be seen in the various way. It may be in terms of strength, it may be in terms of your deflection, it may be in terms of collapse, it may be in terms of a overturning, and many more. The structure must be stable against the applied load. Now, if we talk about the structure must have adequate life, adequate life means what? It is a design life. It is the working life of a structure where the structure is able to sustain the applied load before the failure. So here what we can say, adequate means it is being serviceable for a larger time period. Okay. The structure must not vibrate dangerously, especially in the case where we are going to provide machine foundations or the foundation nearby. There is an impact of free vibrations, like we can say impact loading from bridges, or we can say impact loading with reference to the machining activities nearby. So the structure should not vibrate. Resonance should not be there in the structure. If the resonance is more, then what will happen? The structure will go into modal action, thereby making it very dangerous, vulnerable, and cost to the failure. A structure must be easy to maintain. What's the meaning of this? Though we are going to construct a structure which is as per our requirement, but when we design its connection or its aesthetic view or appearance, if we say pleasing appearance, it should be in such a way that it should be looking very pleasant and very easy to handle. For example, in case of bolted connection, there may be chances that bolt and nut get loosened out, and the configuration should be that the one can go and maintain the connections in position. Okay, this is the meaning of the statement which is stated here. A structure must be easy to construct. It should not be a very complicated one. It should be having a simple profile. It should be having a simple geometry so that it can be easily constructed with the locally available material. Now, the part of enough ductility, if I say the part of a ductility, it resembles over the reversible deformation which is being gained by the structure. To illustrate this, let us take an example of a high-rise building, which is subjected to a wind current. Here, what will happen? Due to wind current, the tower may get deflected laterally, get swayed. Okay, but as soon as this pressure get reduces, it should regain its original position. If it's not so, what will happen? There may be a chances of the stresses to be exceeded, and there is a overturning of the structure. So here, ductility implies what? How the structure is going to regain its deformation after the removal of the load. In short, we can say the structure must be elastic, and it should have a elastic behavior in it. Now, let's move towards the next part, which is said to be performance expected from the structure, in which we will see what is the performance expected under the action of the loads. As we know that force is an element which tries to tends to change the state of a body. If it is in rest, it makes it to be in motion. If it is in motion, it's going to be make it into a rest. So this force which appears on a structure appears in various forms. The forms where in which it appears is called as the loads. Okay, the load on the structure. If we want to classify loads on the structure, identify the loads on the structure, we can say there are three general ways to identify it: vertical loads, horizontal loads, and longitudinal loads. Generally, the reference is given to the reference planes. If it is going to act in vertical plane, I am going to call it as a vertical loads. If it's going to act in a horizontal plane, I am going to say it as a horizontal load. If it is going to act in along the length of the member, I am going to say it as a longitudinal loads. In case of vertical loads, all gravity loads can be considered in this one. The very first load which can be nomenclated under the head of vertical loads is the dead loads. This is the load due to the weight of the particular structure. It depends upon the volumetric content of the particular structure component. Live load, it's also a type of dead load, but it's not permanent with the structure till it is in service. For example, the columns, beams, and slabs, these are permanent with the structure. The load will be considered as a dead load. But the partition walls, they are not being permanent with the structure. They can be removed or they can be replaced, or asset loads. They are dead in the form, but they are not permanent with the structure for a long period. That's why we are going to call it as a live load or a imposed load. Similarly, snow loads. This is also not a permanent one, but it is considered in the case where there is a heavy snowfall in the snowfall area. The snowfall, due to heavy snowfall, the snow will get accumulated on the surface of the structure, thereby increasing the weight of the structure. Okay, that's why we have to consider snow loads also. Construction loads. These are also a dead loads, but temporary in nature, which are generated due to the equipment, due to the form works, due to the arrangement which are made to erect the structure. Creep. These creep loads are due to virtue of material property. After a certain age and time limit, there will be a development of creep stresses in the material, thereby inducing additional forces on the structure we call as the creep forces. Now, in case of horizontal loads, if I have further classified it, we can say it's a seismic loads, wind loads, wave loads, hydrostatic, and soil pressure. Seismic loads are the loads which are generated due to earthquake waves. When the earthquake wave strikes on the structure foundation of the structure, it vibrates the entire structure, thereby it develops an inertia forces throughout the height of the building. So these forces, seismic loads has been generated with reference to the earthquake shocks which are being observed by the structure. Similar way, wind loads are there. These wind loads are generated due to the flow of wind current, where we are going to erect our structure across the flow current, and thereby it induces a pressure on the entire structure. For example, if I say here there is a tree, when wind blows, the tree gets sway and then bend down, thereby it allows your wind current to pass away and get back to its position. It's very elastic, but our building can't do so. So what will happen? Building will be subjected to inertia forces at different level with different intensity. So we have to consider the wind loads as an inertia force which is acting along the height of the building. Wave loads, these are generally appear in the structure where they are subjected to the wave currents, like the structure which is resting in sea, the structure which are resting on across the water currents. The wobbling effects will be attacked on the structure, thereby developing a certain forces in it. That forces we call as a wave loads. Hydrostatic and soil pressure. This is generated in retaining structures, like in case of dams. The hydrostatic pressure will be produced due to the storage of the water along the side of the dam, and similar way the retaining walls, the soil pressure will be exerted from the infill which we have put across the retaining wall. The longitudinal loads, if we categorize, this will be the loads which are developed due to the changes in temperature, we call it as the thermal loads. The machine vibrations which propagate throughout the body of the structure, we call it as a machine vibration. And corrosion, this is on the virtue of the rusting of the material, thereby inducing the additional stresses. Okay, this we'll discuss about the other prerequisite in upcoming lecture. Till then, please be at home, be safe. Thank you.